classical physics of Newton and pals reigned supreme for a few centuries. So what were the events that finally exposed its limitations? What was the first thing that suggested there was more to the universe than we had previously thought? This seismic shift was initiated in 1901 when Max Planck solved something called the ultraviolet catastrophe. The problem went like this. Certain objects are called black bodies because they emit electromagnetic radiation of all wavelengths. The sun is an example of such an object, and we can take a look at the distribution of the wavelengths of light that we receive from the sun. Most of it is in the visible spectrum, which is why our eyesight evolved to pick up this kind of light. But we also receive light on either side in the UV portion as well as infrared and beyond. A hot piece of metal will also do this, and this was the way we studied black bodies at the time, noting that the distribution depends not at all on the material, but only on temperature, with the particular wavelength that is emitted with maximum intensity shifting left as temperature increases. This maximum will move into the visible spectrum at around 4,000 Kelvin and above. This is why very hot objects appear to glow, like a hot oven, light bulb filament, or the sun and other stars, because objects at these temperatures emit a lot of visible light, as opposed to something like the human body, which at around 310 Kelvin emits essentially no visible light, which is why we can't see each other in the dark. The problem with the black body spectrum was that classical electromagnetism could not account for it. Mathematical models attempting to produce these distributions were able to fit the data for the longer wavelengths, but they did not predict that the intensity would dip down to the left for the UV portion of the spectrum, as experimental data illustrated. Instead, the math predicted that the intensity would continue to increase as the wavelength decreased, and become infinitely large as the wavelength approached zero. Of course, we know that this can't be true. Otherwise, every time you use the oven, you would get blasted with UV radiation. This contradiction was dubbed somewhat dramatically the ultraviolet catastrophe. In science, if a theory does not accurately align with observations of reality, it must be revised. And so, we realized that classical electromagnetism, as powerful as it is, must have some kind of limitations of reality. It must be revised. And so, we realized that classical electromagnetism, as powerful as it is, must have some kind of limitations in its ability to describe light and energy. As we said, Max Planck solved this problem, and he did so by introducing a concept called quantization. We know from classical physics that heat is just the transfer of kinetic energy from one place to another. In the case of a piece of solid hot metal, that kinetic energy takes the form of atomic vibrations, or oscillations. These vibrations are what generate the light we see in the black body spectrum. Planck proposed that the vibrational energies of these atoms, and by extension, the energies of the electromagnetic waves emitted by these atoms, must be quantized, meaning that rather than being able to take on any value from a continuous series, they can only possess specific discrete values from a set of accepted values. In this way, he developed this expression for black body radiation, where energy is equal to n, which can be any integer, times h, a term we call Planck's constant, equal to 6.626 times 10 to the negative 34 joules seconds, times f, the frequency of radiation. The n value is what results in quantization, as it can only be an integer and not any fraction or decimal in between, meaning that the resulting energies will also comprise a set of allowed values, with anything in between being forbidden. This application of quantization and the accompanying Planck's constant were developed in ad hoc manner, meaning that they were simply proposed for practical purposes, but they allowed for the accurate prediction of the true distribution of black body radiation at all wavelengths, which meant that this constant was more than a mathematical fluke, but a clue as to the fundamental nature of reality. And the fact that Planck's constant is so incredibly small explains why the notion of quantization of energy had not cropped up before. Because it shows that energy is quantized on such an incredibly small scale that the gradations between the allowed values are utterly minuscule, so as to appear non-existent to any measuring apparatus. Energy appears to be continuous to macroscopic beings, such as humans, but on the fundamental level, it is indeed quantized, even though this conclusion was so strange that most scientists of the time, including Planck, couldn't believe that it had actual concrete physical meaning. This was the first time that quantization had solved such a big problem in physics, but it wouldn't be the last. It was the first in a series of developments that would utterly transform the field of physics, and by extension, our perception of reality. While Planck's work solved one problem, it created another. Why is there quantization of energy? This marked the beginning of the quantum revolution. So let's continue and see what happened next. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon.